All right, this next section of differential equations, we're going to be solving differential equations without a given y equals or differential equation, and we're going to be doing some basic word problems. Once again, I'm just going to be talking through how I'm solving these problems as I'm doing them. And in this video, we're going to be using an ansatz, which is if we have a differential equation in this form, dy dx equals a y plus b, then we know that the solution is going to be in this form. So we're going to be using this a lot in this video because we don't want to have to always do the following method. Here's, 7 lines of work. We don't want to have to do that every time. So we're going to be using this idea. I'll refer back to this a few times. Okay, so here we go. Solve the differential equation dp dt equals 2p plus a. So this looks exactly like the ansatz that we just looked at. So, with p being y and t being x, we can just kind of modify what we've got here. And I don't like that we're using a here and I've used a, so I'm going to change this a to an alpha just so that we don't get confused when I'm saying a for multiple, for two different things. I don't want to do that. Okay, so it looks like p is y, so we've already started there. Negative b over alpha, b in this case is a, so negative a, and alpha in this case is 2, so negative a over 2, plus c, and what do we have? E to the alpha x, so e to the 2, in this case t. That's that. That's all we have to do there. So let's keep going. Okay, these are a little harder to follow, but we're going to be looking at these. The whole idea here is basically um, these are rate problems. Differential equation is a rate, and we're basically looking at in minus outs. That's the idea. That tells us if we're looking at a tank and we want to know the rate of change within the tank, we look at what comes in and what goes out. So we're going to model this rate, which they're calling dq dt. Let me actually read the problem before getting into it. So we have 1,540 liters of pure water in a pond, not a tank, and an unknown amount of an undesirable chemical. Water containing 0.01 kilograms of this chemical per liter flows into the pond at a rate of this. Okay, that is our in rate. I'm going to go ahead and put that. So this is 2 liters per hour. That is a rate in. Um, and we're going to do something with the 0.01 also, but let's just leave that alone for now. The mixture flows out at the same rate, so minus 2 liters per hour here. So the amount of water in the pond remains constant. Okay. Assume that the chemical is uniformly distributed throughout the pond. Okay, that's important. Let Q be the amount of the chemical in the pond at time t equals hours. So Q is a mass in kilograms. We're going to write a differential equation for the amount of chemical in the pond at any time. Okay, so dq dt. This rate, I think the units are really important in this question. That's going to be kilograms per hour. The reason I bring that up is so far what we have is liters per hour. So we need to find this in kilograms. So to do that, so I think the rate in is a little easier because it's coming in at 2 liters per hour, and the concentration is 0.1 kilograms per liter. So we can go ahead and multiply that by 0.01. Nope. By 0.01 kilograms per liter. Nope. Kilograms per liter. And the canceling happens very easily there. So I'm actually going to go ahead and start working on our final equation. So we have, this is going to be 0.02. I'm going to leave the units off. Okay, so that's what's coming in. What is going out? We know it's going out at 2 liters per hour, but what is the concentration? So the concentration depends on the amount of chemical we have, like in the tank or in the pond, like the total amount, and the amount of water in the pond, because it says it's mixed, mixed evenly distributed or uniformly distributed. So if we find the kilogram amount and divide it by the liter amount of volume, we should have that concentration. So we do know the whole pond is 1,540 liters. The amount of solid in that pond is dependent upon Q. It's the amount of chemical in the pond. So we will say Q, kilograms. Okay, and there we go. Now we can cancel. We get 0.02 minus 2 over 1540 Q. And that's our answer to A. So I'll just mark that as A. Um, great. And the question B says, how much chemical will be in the pond after a long time? So right now our equation doesn't have any T in it. But we notice that T is in the denominator of our derivative. So we can use the ansatz again, which I will really quickly write. dy dx equals ay plus b, and y is equal to negative b over a plus c e to the ax. So this is our ansatz. And if we do this, we notice that our dy dx equation, which is what we have, if we solve this, we pull that x out. It actually becomes a part of our equation, which is great, right? We want a t and we don't have one. So let's rearrange this. So we have our y is q, so we're going to say q is equal to negative b. So what is that? Well, b in this case is 0.02, negative, over our a, which is negative 2 over 1540, plus c e to the ax, negative 2 over 1540. And instead of x, we have t. So this is t. So this is great. We have our t. I'm going to get rid of the ansatz so I have a little more space. Okay. Set this equal. We can simplify this fraction. It is 15.4. And c e to the negative 2 over 1,000 t. Okay, so this is saying how much chemical will be in the pond after a long time. After a long time, this means that t is going to be very large. A very large value for t, of course, would be infinity. And so let's think about what happens if this exponent if we were to replace t with infinity here, basically. So it would be infinity times some number, which would still be infinity, but it's times a negative number, so this would be e to the negative infinity. So this would be c e to the negative infinity, 15.4 plus this. E to the negative infinity is a limit, and that limit is 0. So this term would go away. So our concentration as t goes to infinity, or after a very long time, is 15.4. The amount of chemical that will be there. And C says, does the limiting value in part B depend on the amount of water that was present initially? Well, the amount of water that's present initially, we can solve this, and it might be good to. Yeah, let's say that there is an initial amount Q naught. Let's say that our initial concentration would be at a time t equals 0, and that concentration would be Q naught. And I'll just show you what I mean by that. 15.4 plus c e to the negative 2 1540 times 0. That time t equals 0, that's an initial concentration. Okay, so this is going to allow us to find out what our C value is. We have 15.4. E to the 0 is just 1, so this is C, so Q naught minus 15.4 equals C. So if we change our initial amount, our initial Q naught, if it's 0 or if it's a very large number, it will change our C value in this equation. But because as t goes to infinity, the term that has C in it goes away, it won't matter. It doesn't matter what C is. The answer that we'll get for as t goes to infinity is always going to be 15.4. For smaller values of t, yes, the initial concentration would matter, but no, doesn't matter. Okay, so that is a rate in a pond. Now we're going to be doing a problem related to falling. And this is a similar idea. We have a rate, total rate. And in this case, instead of in and out, we have down and up. And we'll talk about whether we should do down minus up or up minus down. But let's read. Okay, body mass 3 kilograms is falling in the atmosphere near sea level. V is the velocity in meters per second. Assume that V is positive in the downward direction. So I want my rate to be down minus up. Down minus up. Instead of in minus out. Okay. Down minus up. And we assume that the forces acting on the body are the force of gravity and a retarding force of air resistance with direction opposite to the direction of motion. Okay, so we're talking about forces. And I will really quickly remind you that force is equal to mass times acceleration in general. So we have the total forces acting on the object are going to be equal to the force of gravity minus the force of air resistance, which is pushing our object up. Okay. Force of gravity and the magnitude of the force of air resistance is CV. And here's that constant and the gravitational constant. So we want to find an equation for dV dt. Okay, so right now we're dealing with forces and we have an equation we can work with. And that force equation has an A in it. And the relationship between acceleration and velocity is that the derivative of velocity is acceleration. So that's great. That is what we're looking for, so we can work with what we've got. Okay, so total force is going to be ma. Gravitational force is going to be mg. The force due to air resistance we said was cv. Now we can divide by m. We get g and c over mv. And a we said is dv dt. G was stated as 9.8, C was 0.35, and M was 3. So here's our differential equation. That is our answer to part A. And B says find the equilibrium solution of the differential equation, which is the limiting or terminal velocity. Hopefully you remember from the first video that the equilibrium solution is that solution that as we go towards infinity, we're just going to stay there. It was flat on the slope field or the direction field. So if we have a slope of 0 for any value of t or for all infinite values of t, that would be our equilibrium solution. So we can set dv dt equal to 0, 9.8 minus 0.35 over 3v, and just solve for v. I'm going to do this on the calculator. Negative 9.8 times -3 divided 0.25. So end up getting 84 equals v. So our terminal velocity would be 84 meters per second. And what that means, like in a physical sense, is once we reach a velocity of 84 meters per second, we will not accelerate anymore. So you won't continue to fall faster to the ground. You'll stay at 84 meters per second. Okay. Let's see. Here we are. Very similar problem. Body mass 26 kilograms is falling in the atmosphere near sea level. V is the velocity, body time t seconds. V is positive in the downward direction again. So rate down minus up. Okay. And force of gravity, retarding air force, proportional to the square. This is the difference here. It's the square of the velocity. C is the constant of proportionality. So if we follow what we did last time, we have the F total equals Fg minus F air. And this was MA, Mg. And last time this was CV. But this time we're saying it's proportional to the square of the velocity. That's the only difference. G minus C over M V squared. And we said that A is dV dt. G is 9.8. C, we don't have C. We have 26 is the mass. And this is the differential equation. That's it for A. B says determine the limiting velocity after a long time. Your answer should be an expression in C. Okay, so once again, we set dV equal to 0. So 0 equals 9.8 minus C over 26 V squared. Negative 9.8, negative C over 26 V squared. Negative 9.8 times 26. 254.8 over C. The square root of that is V. Okay. Yeah, so there's our answer to B. If we want to find the drag coefficient so that the limiting velocity is 45, all we need to do is set V equal to 45 and move some things around. 254 over C. So 45 squared. 254.8. Answer. Yes, okay. C is equal to 0.126 approximately. Okay. That is that. It's just a lot of plugging in. Okay. Similar problem. 80 kilogram skydiver jumps out of an airplane. We assume that the force is acting on the body, the force of gravity, retarding force of air resistance, direction to the opposite of motion, magnitude CV squared once again. And we do know C this time. Okay, V is the velocity of the skydiver. Upward is positive. So this time we're going to say rate is equal to up minus down. Okay, that's difference there. Everything else is the same. We have a total force equals to force of air minus force of gravity, MA. This was CV squared. This was mg. A C over mv squared minus g dv dt. And okay, this time we know C is 0.2025. The skydiver is 80 kilograms. We have v squared, 9.8. So, once again, there's a differential equation. Determine the terminal velocity in meters per second for free fall. Okay, so we set dv dt equal to 0. 0 equals 0.2025 over 80 v squared minus 9.8. Okay, this is calculator 9.8. So it's coming down here, 3871.6 equals v squared, square root of that. 560 over 9 equals v. Okay, and when we take the square root of something, it is positive or negative, right? And because we're thinking about falling towards the Earth, before this would be a positive velocity because an object falling towards the Earth has a downward velocity. And in the last two problems, we assumed that the downward velocity to be positive. But here we need to be careful because we've switched it. So up is positive, down is negative. So this would be negative 560 over 9. Okay, I think we're about done. Yeah, okay, here's the last one. So something that I haven't mentioned yet is this. We have a differential equation, and then we're going to plug in specific values. These values, this would be called the initial condition. Okay, we'll see what that requires us to do. Okay, this looks so much like our ansatz. I'm going to write that again. A y plus b. And this ended up being y equals negative b over a plus c e to the ax. So in this case, we find that our solution here would be 3 is A, 11 is B. So y equals negative 11 over 3 plus c e to the 3, not x, but t in this case. Okay, and this is a solution. We would call this the general solution. When we are plugging an initial condition into a general solution, we are finding the what's called particular solution. So let's do that. So when t is 6, y is 10. So 10 equals negative 11 over 3 plus c e to the 3 times 6. So 10 is equal to, let's go ahead and add this. 30 over 3 plus 11 over 3, 41 over 3, c e to the 18. 41 over 3 e to the 18 is c. Okay, so plugging that in for c, we get y equals negative 11 over 3 plus 41 over 3. I'm going to write this like this, e over 18. And we can rewrite this just so that the e's all together. And let's put everything over 3. So negative 11 plus 41 e to the 3t minus 18 over 3. Okay, so we use an ansatz to solve differential equations where we weren't given a y equals or a function in order that we were going to plug in. And we did some word problems associated with rates in, rates out, force of gravity down, force of gravity up, also, and air resistance. Yeah, so hope to see you in the next one.